I'm going to talk a little bit about stuff that I think will be obvious to everyone here, might not be obvious to people who are not programming in Rholang, but makes the connection to why I'm interested in the linear algebra side, connecting the linear algebra side of NKZ to Rholang. So let me just do a screen share. So I think everyone here probably already gets this, but one of the things that's really nice about the way Rholang operates is, you know, because we've made all data values into first-class processes, we can do fun things like this. So if we want to represent linear algebra in Rholang, vectors are obvious. We might first start with something like this. So at I, we put the ith value of the vector. Now, of course, that doesn't quite work because then we couldn't have different instances of vectors, right? But if I just make some salt here, and then I add the salt to the index, and I make sure that, you know, whoever wants to access this particular vector has the salt, then they can now access each of the entries. Right, so at each xi, there's the value of the ith value of the vector. Is this clear?
Yeah.
And while this composes, right, so I didn't say what the values are, right? So I could put vectors as the ith value of the vector v. There is obviously a more efficient approach. So for a matrix M, I can do the same trick. So I make some salt, and then the ijth entry of the matrix is put out on the salted ij name. So we can the thing. So part of this is just beginning to realize that Rholang is notationally very compact and efficient, right? So the ability to write down the matrix is roughly the size of the matrix itself. So the access, installing, updating, and accessing is roughly as efficient as linear algebra notation itself. To formalize this, to investigate this a little bit more, we can see that if I want to define the inner product of two vectors, then I just use the accessors, right? So I'm assuming that I have an operation ID for vect, which will give me back the salt, and that's relatively straightforward to define. I leave that as an exercise. Then we have the for comprehension, which accesses each of the different values in each vector, and simply outputs the corresponding sum. And one of the things that this well, let me go in a particular order. So obviously you can generalize this to matrix multiplication. So again, we access, so if M is an M by N matrix, so M rows by N columns, and that's M1, and M2 is N rows by P columns, then these accesses will access the entries in each of the matrices, and this is the constructor which gives us the fresh matrix, right? So for ij, we do the sum over the inner k's, and we just make some salt to make sure that that has that we've got an instance of the matrix. So one of the so again, notationally, it's within the ballpark. And this extra information here. So typically this is what you would expect. Like if we go to the Wikipedia page, right? Here's the notational size, right? So they have to write down.
Sorry, Greg, we don't see this screen.
Oh, thank you. Yes, sorry about that. Just fix that. So if we go to the Wikipedia page, right? Here's the definition for the ijth entry of the matrix product. So they also have to write down sort of the indexing scheme, right? Here's again the sort of notational weight of matrix multiplication in standard notation, and we can compare that to the notational weight here. So it's same order of magnitude, right? But there's a lot of extra information here that is explicit. And the information that's explicit is that we have talked about what are concurrent accesses. So I've used the Rholang 1.1 notation. So both here and here, we've marked which accesses can be done concurrently. Right, so this access is running in parallel with all of these accesses, which are running in parallel with all of these accesses. And so the point I'm trying to make is that we didn't do anything, like Rholang wasn't designed specifically for linear algebra calculations, and yet it provides a very compact and efficient notation that tells us precisely where the concurrency opportunities are. And so that it, like the thing with if you write this down in Java, so you have roughly similar because of their array notation. You have roughly similar, and that's the array notation is specifically designed for that, right? It's out. You know, you can imagine Java without array notation, right? So it's a feature that is added to the core language. Here we've added no features to the core language, right?
Yeah.
And yet we have notation that is you know, roughly as efficient as standard mathematical notation. But in Java, you can't see unless you already have inside your mind a mental model of where the concurrency opportunities are. You can't see it from the notation. Here, we have a notation that is the same size, but where we can explicitly see where all the concurrency opportunities are. And so the point is that then when if you go back to if you recall our discussions from last week, where we talked about that MPC in the head paper that used a lot of linear algebra in order to do the computations. The reason I want to get those nice and crisp and related to the message passing is because we have the ability to reflect those crisply and succinctly in row calculus, the Rholang. So I just wanted to make that explicit because I know that I carry a lot of information around in my head that I often don't make explicit. And so I thought it would be useful to point this out. So another point of comparison is if you look at the way Rholang encodes JSON, right? It's a one-for-one encoding. So Rholang does, both JSON and linear algebra, right? So either end of that spectrum, from objects to matrices and vectors and things like that. So this is I think this is a clear indication that the notation is well suited for an extremely wide range of computational phenomena. And so when we, so that's already a good set of tests. But then the point is that you can go, once you got notation that allows you, there's a principle here that is always important to me. I want to be able to unburden my mind with having to carry around a lot of extra, a lot of extra implicit information. So, for example, when I'm looking at Java code, I have to carry in my mind the state of the stack, the state of the heap, the state of the environment, and the state of the threads that are locked, the threads that are running, and which ones are locked. Right? None of that is in the code. Right? The code doesn't represent that. By contrast, Rholang gives you everything that is around for running is in the code. There's nothing in the code there's nothing missing from the code in order to simulate in your mind what is going to be executed. And as a result, there's a lot of cognitive burden that's lifted. So the same thing goes when you talk about particular subdomains. So here, when we're thinking about linear algebra, Rholang gives us this ability to not have any implicit information lying around that we have to burden the mind with. We can just stare at the code, and the code will support all of our thinking. Right? It provides an extra level of, you can externalize what you're holding in your mind, and then just reason about the form that's in front of you. Does that make sense as a principle?
Oh yeah, very much.
Cool. So this is why so there are a lot of threads here that are woven together as I'm going after the ZK stuff, the ZKP stuff that's related to the multi-party computation. Rholang is specifically designed for multi-party computation. And at the same time, Rholang supports the linear algebra operations directly. And so that's why I'm quite keen on teasing this out and getting a good representation. So that's roughly what I want to talk about today. Any questions or comments?
Well, I just want to notice that this seed, or like ID of a specific matrix, it looks like we have the variable that is that is shown on the wiki page is like inside the matrix itself.
It's inside
because,
it's inside it's inside the addressing scheme. It's not inside. It's not inside. So the values are to the right-hand side of the bang, and addressing is to the left-hand side of the bang. So it's actually there, right? A 1 1, B 1 1.
Yeah. Exactly.
So it literally lines up precisely with the notation.
So, Greg, in terms of actually writing this in Rholang, would we have a shortcut? Even though this is directly representable for large matrices, this may not be.
I mean, this is legal. This is legal Rholang 1.1.
Yeah. Mm-hmm. No, I get that, but I'm saying if I were to actually do a big matrix, 20 by 20 or 20 by 30 or something like that, writing all of this would still be cumbersome, right? I mean, this may be how it is translated, but maybe there should be a short notation that then gets translated to this.
Well, you can translate all of the array notation into this.
Okay.
Yeah, that's kind of the point. These are definitions for the array notation.
Yeah.
Right. So so the left hand, this is the thing that you would write in Rholang, and this is the thing that you would write as your shortcut. Right. So this is your constructor. This is your constructor.
Mm-hmm.
This is your operation. This is your operation.
Okay.
Yeah, so it gives people a high level of compression. But the point is that when you're doing linear algebra, you are writing this stuff down, right?
Yeah.
I mean, what people do is they then move to the operational. They go from the pointed notation to the point-free notation, right? And that's what's happening here, right? This is the pointed notation. This is the point-free notation. We're no longer looking at the entries over here.
Yeah.
Cool. I wish I had more to tell you about MPC in the head today, but I had a funeral over the weekend that I had to attend to. So that kind of cut into all the research time. Any other questions or comments?
Thank you. That's nice.
Cool.
Yeah, it's clear.
Awesome. Very good. Well, I will yield back the time, and I'll see you folks in the Dev Stand-Up.
Thanks, Greg.
Thank you.
Sure.
All right. See you.